In this video, we will look at three techniques that do not have an explicit name but are very useful in solving binary strings problem that involve subarray, subtree, or a vertical path on a rooted tree. Let's start out with the simplest version of the problem where you are given a binary string. Let's say it contains zeros and ones only. That's why it's called a binary string. And you have to convert this binary string into a string containing all zeros. And how do you do that? Because some of the bits are set to 1. So you are allowed to do certain operations, and in one operation you can select one subarray and you can flip all the bits inside this subarray. So 0 gets converted to 1 and 1 gets converted to 0. And your goal is to minimize the number of operations that you have to do such that the final resulting array is a string of zeros. How do you solve this problem? So to solve this problem, you will need some ideas from the bit manipulation world. When I say that you are allowed to flip all elements, this is a well-known fact that flipping is equivalent to XORing the entire subarray with 1. So if you are not aware of this, like maybe this might also be something that is new to you, but this is a very well-known trick that if you want to flip everything, then you can equivalently express it as, if you want to flip x, you can say that x XOR 1 flips x. Why is this true? It's very easy to see, because 0 XOR 1 is equal to 1. So you see that 0 got flipped and 1 XOR 1 equals to 0. It means 1 got flipped. So you can reword the problem and say that in one operation, you can select any subarray that goes from L to R and you can XOR all the elements with 1. Okay, so far so good. But how does this transformation help us? So this does not help us right away, but at least we know that we have to do some operations with XOR, and XOR is a well studied field, so maybe we can utilize some tricks from the world of XOR. So now let's see what other transformations that we can do. So in one subarray, can be a lot of elements. So if this is index L and this is index R, there are a lot of elements for you to process, and your brain might not be able to process all of these elements because you have to keep track of everything, because everything gets flipped at the same time. So can we do some other transformation that will help us go from subarray, like visualizing a subarray with so many elements, to just visualizing some one or two elements? So is a transformation possible? So to do that transformation, you can use the concept that you must have used in the difference array trick. So what is the difference array trick? That trick you must have learned when you are allowed to add a certain delta in a range L to R, and you are given a lot of query, wherein each query, this is query 1, you will be given a delta 1 and you have to update all the elements in this range to add delta 1 to all the elements in between. So how do you effectively process all the queries? You say that instead of maintaining the original array, you now maintain the difference array between all the elements. And what does difference array looks like? So difference array is nothing but d of I you maintain as a of I minus a of I minus 1. That is, instead of tracking this original array, instead of tracking this a, you now maintain a d where d of I, this means difference between this and this. So a of 1 minus a of 0. Similarly, this is index, let's say 2. This means a of 2 minus a of 1. You maintain it in the difference array. So what is the benefit of the difference array in this problem? The benefit is that when I tell you to add a certain delta to all the elements of the range, any two neighbors, suppose this and this are neighbors. If they are completely inside the subarray, then their older difference was y minus x, but their new difference would be y plus delta minus x plus delta, which is nothing but y minus x. So you see that this leads to something known as invariant. So all the elements that are inside the subarray, they will remain invariant. Their difference will remain invariant. So what will change? The only thing that would change is that, let's say what would change. So if you have selected this subarray, then we have concluded that if both the neighbors x and y, if they are inside this subarray, completely inside, then their delta is not changing. But what about the boundary points? So the boundary points, if this element is, let's say, p, and this element is q, so their previous delta was p minus whatever is on the left hand side, and the new delta would be, new difference would be p plus delta minus whatever is on the left hand side. And similarly, what about this element on this, after this boundary? So the previous delta was whatever this element is minus q, and the new delta would be whatever this element is minus q plus delta. So you can see that adding a certain delta to a range is equivalent to adding a delta over here and then subtracting that delta over here. And this is how we were able to solve the subarray updates via the difference array. So can we use that same trick in this problem? And this problem now says that you are allowed to select a subarray from here to here, and then you can apply this operation on all the array elements. So you have to do this XOR1, this XOR1, and so on. So naturally, this suggests us to use the difference array, but this time the difference will be equal to XOR. So you define d of I is equal to a of I XOR a of I minus 1. Now let's see whether this d array remains invariant or not. So again, let's start with two elements that are completely inside the subarray. Suppose this element is x and this element is y. So what is the d value at this position before the before selecting the subarray and flipping it? So the d value would be y or x. But after the flip, it will become x or 1, and this will become y or 1. And the XOR between the two elements would become x XOR 1 XOR y XOR 1, and 1 XOR 1 is 0, so the result is x XOR y. This means that this difference array is indeed an invariant, and only thing that would change are the boundary elements. And you can see that since you are doing a XOR over here, so the d of this entry would change, because if this was p and this was q, so the old XOR was p XOR q, but the new XOR would be p XOR q XOR 1. So this means that flipping a subarray is equivalent to changing two elements in the XOR diff array. Let's call that as the XOR diff array. XOR diff array. So it is equivalent to changing two elements in the XOR diff array by XORing them with 1. So this element and this element. Now, how does this help us? So you can notice that there is a bijection between the XOR diff array and the original array. So let me write that down. So there is a bijection. And what do I mean by bijection? Is that if I give you an array A, then it will have a unique XOR diff array. Why unique? Because we have a special unique formula for computing the XOR diff. So this means that solving the problem on A is equivalent to solving the problem on the Zordif array. And in the Zordif version, all you have to do is you were given an A that contained a long binary string, and let's say you have computed the Zordif array. Zordif array, and this contains this binary string 0 1 0 0 1 1 0 1 0 0 1 1. Now what will be the minimum number of operations? So you know that in the Zordif array you are allowed to select any two elements and then flip them. So of course you would select these two one and flip them so that they become 0, and then you will select these two ones and flip them so that they become 0, and then you will select these two elements and you will flip them so that they become 0. So you can see that in this version it is very easy to prove that the answer is frequency of 1 by 2, or basically you can say sum of all elements by 2. So you see that previously this problem looked very difficult because you had to deal with subarrays, but once you did the transformation for Zordif, then the result was clear that the optimal strategy is to pick up any two ones. They will create a subarray in the original array, and then you flip these two ones. Now, so far so good. A lot of you might already be aware of this technique, but in the next part, let me discuss the tree version. So in this version also, you are given a tree, not necessarily a binary tree, and each element is either 0 or 1. So this is either 0 or this is either 1. So any element is a binary value on each of the node. One value is written. And in one operation, you are allowed to select any node. Suppose you select this node, and you are allowed to flip the entire subtree of this node. So you flip all the values in this subtree. This means that you XOR all the values with 1. Now you have to find out the minimum number of subtree flips to make all the node have the value 0. So again, how do we solve this version of the problem? Remember that we are trying to find some transformation that will maintain most of the things as invariant, and it will only touch one or two elements. So this might be a bit harder to come up with. So I'll just tell you the transformation, and then you can convince yourself why that is correct. And in fact, the goal of this video is for you to learn new techniques, not to develop them. So I'll tell you what the transformation is. So let's define this time, let's define d of I. So there is no I anymore, there is a node. So let's define d of node is equal to A of node XOR A of parent of node. Now let's see whether this thing remains an invariant when you flip an entire subtree. So we are saying that the d value at this location, or we are saying that the d value at this location is equal to the XOR of this and the parent this. D value at this location is the XOR of this and this. Now will this thing actually remain invariant when you flip an entire subtree? Let's check that out. So suppose you have selected this subtree to flip. Suppose you want to flip the subtree rooted at this element. Then let's mark all the nodes that you have flipped in yellow. So let me color this as yellow, color this as yellow, this is yellow, this is yellow. So color all the nodes in yellow, all the nodes that have been flipped. Now you can see that for any node that does not touch the yellow node, their Zordif will not change. So their d value will not change. Why? Because for this node, the d value would be equal to XOR of the value over here and over here. But since none of them are colored yellow, means none of them have changed. So their d value will not change. So we only have to worry about the edges that touch at least one yellow node. Now there are two kinds of edges. One is the inside edge. So this is the equivalent of two consecutive elements being completely inside the subarray. and 1 is the edge that crosses the boundary. So this is the edge that crosses the boundary. So now let's see what happens to the edges that are completely inside. So for example, consider this edge. You will see that the previous value was, suppose this is x and this is y. So the previous value at this position must have been x or y, because by definition you maintain for each node d of node is equal to the value at that node or its parent. But the new value would also be x or y. And why is that? Because both the nodes are colored yellow. So this edge has both yellow nodes. This means that both of them have gotten flipped. So it had become x or 1 and y or 1. So if you take their XOR again, 1 and 1 will cancel out. So this means that if an edge has yellow nodes on both the sides, then its XOR will not change if you use this definition. And you can see that all the nodes inside the subtree, all the edges inside the subtree, all the edges have the yellow nodes on both the end. So XOR for any of them will not change if you have this definition. The XOR for only one node can change, and that node is the one that crosses the boundary. So this is the subtree and this is the yellow node, and you can see that if the number written over here is A and the number written over here is B, then the XOR value for, then the D value for this node must have been previously A XOR B, but now it will be A XOR 1 XOR B. Then this means that doing the operation on a subtree is equivalent to just taking a node and flipping it in the transformed version, and the transformation is for each node you write the value as not A of node but A of node XOR the value at the parent node. So what will be the answer to this problem? Answer is simple. You do the transformation. You do the transformation, and the answer will be sum of all ones, or let's say frequency of ones in the new tree. Why is this statement true? Because in one operation you can only flip one element in the transformation, we have already seen. So if there are k nodes with a value 1 written on it, you will have to do k operations to set them to 0. So far so good. We have solved the subtree version. So you saw that we started out with a very simple idea, which is the difference array trick that you have already seen in arithmetic for adding a delta. Then we converted that trick to the XOR diff array, and that helps you solve the flipping of a subarray problem. And then we converted that same trick to flipping an entire subtree. Now for the last part of this video, let me show you a final trick that helps you solve a problem that says that in one operation, again given this binary tree, in one operation you are allowed to take any downward path starting from root and flip all the values on it. Now this is something, now of course here if you try to apply the same definition that we did earlier, if you try to apply this definition, this will not work anymore, and you can do some case analysis to see why it will not work. Because if you define this as node XOR parent, then a lot of entries might change. So how do you, in case you are not convinced, let me show you why this definition does not work. Consider this node and this node and this node. You will see that after doing the flip, this D of node, the formula for this node will be affected. This node will also be affected because a lot of parents for a particular node is changing on a downward path. So that's why of course this formula will not work. So we have to be a bit creative with it and come up with another transformation that will keep a lot of the things invariant and only change one or two things. So it's a bit difficult to come up with by yourself, and like I said, we are here to learn. So I will tell you the formula and then we'll see why that transformation is correct. So the transformation this time is you define D of node is equal to A of node XOR A of A of child A of child. Yeah, you define D of node is equal to XOR A of something like this. XOR child 1 XOR A of child 2 XOR A of child 3 and so on. So you see that the idea is same, but we are just flipping the narrative. So previously we said that for the subtree version, for this node, we said that take the XOR between the edge that leads upward, and this part will remain invariant. But this time we are saying that for any node, instead of taking the path that is to the parent, for any node, you now compute the XOR between this node and all of its children. So for this node, the D value would be the XOR of this, this, and this. Now, why would this remain an invariant? Let's see. So this time again, let's track this particular path. Suppose this is the downward path that we have chosen, and prove to me why this D of node, wherein for each node you define D as the XOR of this node as well as the XOR of all the children that it has available. So prove to me why this number will remain invariant except for the edges that cross the boundary. So let's see all the edges that do not cross the boundary. Okay. So first of all, let's look at all the edges that do not have any element. First of all, let me color all these inside nodes as yellow. Okay, color all these nodes in yellow. Then if you look at any edge, if you look at any node that does not have a yellow children, then their D value will not be affected. So the D value can only be affected if that node has a yellow children, because the D value for a node depends only on the children, does not depend on the parent anymore. So the D value of this might be affected, D value of this might be affected, D value of this might be affected, D value of this might be affected. But how will it be affected? Let's see. So this is the last element. Now you can see that since you are traversing a downward path, then all of its children must be outside that subarray. So you can see that all of its children is outside of the subarray. So the D value of this will flip for sure, because D value of this is value at this node, then the XOR of the value of this node and the XOR of the value of this node. But these two nodes have not changed. So this one is flipping for sure. But what about this one? So for this one, you will notice that all of its children are outside this bounding box of red color. So if this is the bounding box, then you will see that all of its children are outside. There can be only one children inside. Why only one children? Because you are only allowed to take a downward path. This means that one children is inside. So the D value of one of the children has been XORed by 1, but the D value of itself has been XORed by 1. So there will be 1 occurring 2 times over here and they will cancel out. So if this is an internal node, this XOR value for this will not change. Similarly for this, only one children can be inside and all the other children must be outside. And since the XOR value of this is changing and XOR value of one of the children is changing, so this remains invariant. Same for the root. One children is outside, many children are outside, but only one children is inside. And since the value of this node is changing and this node is also changing, so they cancel each other out. So this means that this property remains invariant except for the last element on your journey. So this means that if I ask you to if you start with a binary tree, let's say if you start with this binary tree, and if I ask you to flip a downward path in one operation and you have to make all zeros, then what is the minimum number of operations that you have to do? You just transform that tree to this D tree, and in this tree you can see that in one operation you can only select one element that is set to 1 and you can set it to 0. So again the answer will be sum of the frequency of ones in this transform tree. And why are we doing all of this transformation? Because you will notice that all of them are bijections. That is, if you define this D definition, then you can recover a tree from this definition and you can create a unique D tree from this definition. So just to summarize the video, we just saw a trick that tells you that if you want to ever, the next time you encounter any problem that asks you to flip a subarray, just convert it to the XOR diff array and your life will become much simpler, because then you will only have to flip two elements. That's good. Then we also saw that the next time you encounter a problem that asks you to flip an entire subtree of a tree that contains zeros and one, just convert it to another tree where the value on each node is equal to the XOR of this node and XOR of its parent. So just convert it to this architecture. And the third trick that we saw is that next time you are dealing with a problem that asks you to take a downward path and flip all the elements on this downward path, to solve it, just take this tree, create a new tree, and in that new tree the value written at each element will be equal to the XOR of that element and XOR of all of its children. And in that tree you will now only have to flip one set bit to a 0 bit. So that was it. That was the 3 new techniques that I wanted to discuss in this video. Let me know if you liked them and let me know your thoughts in the comment section. And if you need any practice problems for this, there is a problem on code forces, but this just appears as a sub problem of it. But if you still want it, I will link them in the comment section. Thank you.